the endlessly cascading. Yeah, because there are two. There's one from the recorder and one from the screen. I like it, actually. I don't mind having things mess with my head, as you might guess. Okay. Great. So now we have our units of distance and we have our units of time. Basically, we'll use normal units of time, except that time more or less extends to the 14 billion year range. And beyond that, we're going to have trouble asking and answering questions about the history of the universe. So now we're going to take the bold step of dividing them and talking about the speeds of these things going through the cosmos. So everything's moving. We have access, like just because we live these short, pathetic human lives, to things like months and years. But everything is moving. We just tend not to notice it on a day-by-day basis or year-by-year basis. Even just the precession of Earth, which is a very local thing, it took, sort of civilization length time, 6,000 years before people are like, hey, wait a minute, something's up, and the seasons aren't quite appearing where they should be. So we'll talk about how we're going to refer to motion, speed and velocity, like precision and accuracy. They're two different things, and we got to parse them. And then introduce the problem of motion, not because we don't know the answer to the problem of motion, but because it's really like this... It's kind of a hinge on which all of this Galileo, Copernicus, Ptolemy stuff hinged, where people, one of the reasons people refused to believe that the Earth was in motion around the sun was, no way, we can do the calculation, and we seem to be moving pretty fast, and I don't feel like I'm moving at 31 kilometers per second. So it almost doesn't merit a reminder, because we talked about it like an hour and a half ago, but this is the day, right? So this is the location of the South Pole is pointing in this direction. We'll give this its cosmic name next week, the South Celestial Pole. It's easy to remember. The month, this is a picture taken from space of the orbit of the moon around the Earth, and that takes a month. And we can use that as a timepiece. And we have a couple of ways of using this as a timepiece. We can use the seasonal calendar, where we just notice that we're pointed in the northern hemisphere. We're pointed away from the sun, so the sun appears at a different point on the horizon when it shows up and when it falls, when it sets here than it would be in June, when in the northern hemisphere we're pointed towards it. That's the seasonal calendar. Or we can use the background of stars, so that would be the sidereal calendar. And that got us through here, right? But again, everything else is in motion. So all these planets are orbiting, and they have their own planetary years. All these planets are tilted. They have their own seasonal effects, too. In fact, there's a spacecraft, Cassini, which is orbiting Saturn for long enough that it's just about to get ready for spring on Saturn. So when Saturn is starting to point more towards, in the northern hemisphere at least, point more towards the sun. So people are excited about that. And there's seasonal weather on these things, too. So it actually generalizes. And then motion, and at the background of what seems like it would be pretty hard to detect, actually a pretty easily detectable motion of galaxies. So we'll just go through, and now we'll put some numbers on that. Before we do that, we have to have a little physics lesson. You guys ready? Okay. Speed is distance over time. So I travel some number of kilometers in some amount of time. I just divide them. That's speed. This is what shows up on, I think this is in kilometers per hour, I hope. That's what shows up here. What isn't on the speedometer of your car, actually? So a piece of information that it doesn't tell you, which we actually do care about. Yeah, so there's a difference in between these two terms, speed and velocity, and from now on we care, because they let us know, one, how fast you're moving, but also where and what's causing it. So speed, just divide the distance by the time. What I don't know is where this car is driving, and a couple of, can't see it there, but it's on the slides. It's a couple of useful rearrangements, thank you. For how long will it take something to hit me? Will I just take the distance divided by the speed, and then how far is something traveled? Speed times time. So for the last page, you'll see those. Okay, this is a new thing. We have velocity, and now you're on the hook for knowing the difference in between these. Is your velocity is your speed in the direction in which you're traveling. So you think about it more like an arrow. So an arrow, like a vector, if you've been through vectors, is it not only has a length, but it also has a direction. So in this case, the speedometer of this car might read 200 kilometers per hour. I mean, it's an old American car, so I know it doesn't, but let's just pretend for a second. Let's say they're driving east. So that's a velocity, right? So the 200 kilometers per hour is their speed, but then the 200 kilometers in the easterly direction is their velocity. So now you're liable for this. And now we can get into this set of levels of the cosmic address and start putting some numbers on it. So we're spinning on our axis. That's the motion associated with the day. In Seattle, that's about 800 kilometers per hour. So me just standing here because the Earth is spinning and the Earth is pretty big, I'm moving at 800 kilometers per hour. You guys feel it? Yeah, so you drink cough syrup before class, maybe. I don't know. So same thing, we're pretty far away from the sun. We spin around once every year. If I put a number on that, that would be like 31 kilometers per second. You'll actually calculate it yourselves. If I looked at the differences in the stellar motions, those are going at somewhere in between 50 to 100,000 kilometers per hour. So all of the stars are moving, and the velocities are random, so there's no, at least in our local neighborhood, they're kind of random beehivey. Our solar system and all of the other stars in our neighborhood, they are actually orbiting around the Milky Way galaxy. It takes about 250 million years to execute a full orbit. So that's at almost 1 million kilometers per hour. And then we have some random velocities with huge speeds in the local group. That's 300,000 kilometers per hour. And then this, once you get outside of local groups and into superclusters, you experience what is so-called Hubble expansion. And everything is moving away from everything else. And the farther something is from us, the faster it's moving away from us. And in some cases, up to the speed of light, if not larger. So there's a lot packed in that statement. So why is everything running away from the Milky Way galaxy? What did we do? And two is, how on earth are you having things move faster than the speed of light? So this will be our kind of grand finale in terms of just like understanding the physics of what's going on. Okay. So just for the sake of putting these down in numbers, is that this motion, 800, 1,000 kilometers per hour, that's impressive. I mean, if I were to think about that as a speed on the globe itself, that means that I would get from, this side of the United States to that side of the United States in a couple of hours. So that's like riding in a jet plane with the top-down speed, right? It's fast. Actually, about twice as fast as that. In the astronomical context, so we're orbiting, and this is about 31 kilometers per second, 100,000 kilometers per hour. I like the 31 kilometers per second better, because you're like, that's here to Tacoma in a second. And I know some people have that commute, so you could just sit there and think about how awesome that would be. So now we can put on, and this will be a legitimate way of talking about velocities, is let's say I were to ask, I gave you the speed, so we're going 100,000 kilometers per hour, or 31 kilometers per hour or per second. Now I'm going to ask you what our velocity is. So let's say it's March 21st, and I know that if Earth had a speedometer, that speedometer would read 31 kilometers per second. What direction are we traveling in? And what's the most reasonable way of pointing that out? So if I'm going around in a circle, my velocity is going to be like tangent to the circle, so I'm kind of going this way. What do you think a reasonable way of describing the direction part of that velocity would be? Towards Ophiuchus. Yeah. And it seems like it's kind of a dodge, but it turns out that we'll actually do this all the time, is we'll refer to directions with respect to constellations, because it's very convenient to do so. Okay. Does that make sense to people? So tangent and March 21st, my velocity is going towards Ophiuchus. What about June 21st? I'm traveling at 31 kilometers per second in what direction? Towards Aquarius. Remember, these are all wrong because I think this isn't corrected for the precession thing, but yeah, in this picture at least. Good. So we'll come back and do this next week formally, in the sense that we'll figure out the right way of pointing at things in space is through constellations. I want to mention one thing before we adjourn, is this. So this is the problem of motion, in the sense that all of these numbers are pretty extreme, right? 30 kilometers per second, 100,000 up to 1,000,000 kilometers per hour. Hubble expansion faster than the speed of light. So if we're moving this fast, why aren't we like ripped off the face of the Earth? So we're moving this fast, why don't you feel it?
Because the force of gravity is greater than the force of the speed moving us from side to side or whatever.
So one suggestion is that gravity is keeping us there, and if we turned off gravity, all of a sudden we would like be flung off or something like that. Okay. So the second way of phrasing this is if we're hurtling through the cosmos, in fact, these stars, their peculiar velocities are 50 to 100,000 kilometers per hour. Why don't we just wait a long enough time where we would see something? This is this cave in Guam where they actually there's a recorded supernova in this too, but there are these old pictograms of what the people who settled on Guam, which is 4,000 to 3,000 years ago, they used their particular constellations. Orion is so characteristic that they used Orion. This is Orion 3,000 years ago. There's similarly old depictions of Orion carved into pyramids, or drilled into the sides of pyramids in ancient Egypt. The stars in Orion have not shifted position in 4,000 years. They're all moving relative to each other, 100,000 kilometers per hour, and 3,000 years is a lot of hours. So why don't I see this? So these are the two problems of motion. And one, I think we could probably get the answer to. The physics, why don't you feel it? I'll give you the bad idea, and then we'll talk about the good idea next week. So why isn't Orion flying apart, even if you give me 3,000 years? Yeah, light years are so absurdly far away, right? So if you see a plane in the sky and that plane's really far away, it just seems to cruise at a very slow apparent speed. These things are so absurdly far away that even if you have them moving at 100,000 kilometers per hour and give them, 3,000 years worth of hours, they don't seem to move apparently. So this is just a gut feeling about how ridiculous the light year is. It's an extremely big distance that really just doesn't have any intuition in regular earthly life. So one wrong answer to this, and this is kind of what we'll phrase and then pick up with, is in the Dark Ages, for about 1,000 years in Europe at least, people said one answer to the problem of motion is that we're not moving and the rest of the cosmos is just centered on us. So we're at the center of the universe, which feels really nice, doesn't it? Yeah. And this got resurfaced twice, actually. You'd think people would get better. But once we settled that, we're going to use motion basically as a physics experiment. So if you can convince me that something's moving, I got to tell you why it's moving. So if you convince me that everything's moving in the same direction around the sun, I've got to come up with a theory of the solar system that explains that. That will be Kepler's laws. If I see a whole bunch of stars that are moving around a mysterious dark patch of sky in Sagittarius, why would a whole bunch of stars be orbiting a patch of darkness pulled around like faithful dogs? So this is 5 years of data. So all of these stars are spinning around. What on earth could possibly be doing that? Supermassive black hole. And then if you tell me that the stars in a galaxy don't spin the way that the measured matter spins, I've got to tell you, well, there must be something we don't see. The motion tells us about dark matter. And then finally, if I can't make this latte foam of the universe without seeding in a particular type of dark matter, so I can't explain the motion without some new physics, this is the only way we're going to do things, is we can measure motion, and then we're going to use that motion as our big physics experiment in the cosmos. So at the end of this, we'll use the motion of things to tell us that there must be dark matter, and the acceleration says there must be dark energy. So this is why we care about velocities. And it's really the only thing that we can ask questions about. So it's kind of hard to take a galaxy and put it in a jar. So this is why we care about motion. And it starts very simply, right? We'll just use it to piece together where our solar system, or where Earth is at the center of the galaxy, center of the universe or not. But then we'll get out here using the same ideas. Okay? All right, I will see you guys on Wednesday. And feel free to bring questions about exercise 1.
Yep. So, what's the asteroid belt?
So the reason